Welcome, atoms and isotopes. Now, this is a video actually made for physics students. So if you've taken chemistry in the past, you will understand many of these topics. Now, this is kind of the introductory video when students in physics, so in particular in foundational physics, so kind of grade 11, sometimes in grade 12, now sometimes it might be in the college or university level, who are walking into nuclear physics or nuclear energy. They do have to understand the concepts of atoms and isotopes. Now, we forget these concepts, so do I, okay, at times. But these particular concepts are super useful. This is just an introductory walkthrough, okay, in terms of a video on understanding the nucleus, right? Understanding protons, neutrons, nucleons, isotopes, okay, and so on. So the reason why you want to understand these topics is because if you do talk about nuclear energy of any kind, so nuclear physics, nuclear energy, you do have to understand the nucleus and kind of have to understand the particles. Now, you can go very deep in nuclear physics. This is just an introductory video, okay, on those topics, and it's meant for students in introductory physics. All right, let's get started. So the first item is, in physics, and of course chemistry, which is just a small branch of physics, okay, you do study the nucleus, which is really nothing else but the center of an atom. And it's extremely dense, okay? Now, dense in comparison to what is externally, okay, flying around, which are the electrons. So the center of the atom, okay, or the nucleus, is made up of kind of two components, protons and neutrons. Now, it is rather interesting that when we define these things, okay, in terms of protons, so it is the main topic, okay, of discussion within chemistry, and very often, and I'll do the same thing in here, is that protons, for instance, are defined as positively charged particles. Now, what is very interesting is that you really talk about positively charged particles, okay, if you understand, okay, the concepts within electrons and protons. So it's very circular, okay, in a sense. Now, the nice thing is that if you are walking into foundational physics, you most likely have had a little bit of science background, and you probably have run into this proton and electron in the past. So I'm going to just leave it, okay, and say that a proton is a positively charged particle. Now, one of the key things in protons is the fact that it defines for us the actual element that we have. So when you talk about carbon or hydrogen, okay, boron, okay, gold, okay, silver, okay, titanium, any of these elements, it is actually the proton that defines that element for us. I'll say a little bit more shortly. Now, in terms of neutrons, well, neutrons in general, they do not have any charge on the particle itself. So protons are positively charged, but neutrons are neutral. There is no charge. And yet both of these are within the nucleus. Okay, so they're combined together and stuck in a dense, okay, center of the actual atom. Now, protons and neutrons have the same mass. So they have the exact same mass. And as you keep moving along, okay, and as you study physics, you're going to get into masses, especially if you get into electricities, magnetisms, and so on. So we're going to need these masses. Well, protons and neutrons have the same mass. So in terms of matter, okay, they constitute the same amount. Now, when we talk about protons and neutrons, very often, okay, what we will say is that when we're talking about the nucleus and the particles inside, well, those particles are indeed protons and neutrons. And we will define, okay, or at least discuss these in combination as just saying nucleons. So from the nucleus, okay, so nucleons, okay, are just particles that are within the nucleus. And which two particles are within the nucleus? Protons and the neutrons. All right? So we have an atom, and inside, okay, of that atom, in the center, we have protons and neutrons. Protons are positively charged, neutrons are neutral, no charge at all. Now, if you dive into electrons, what is interesting here is that for electrons, this is the component which is flying around the nucleus. Now, there are many models that you have within here, but you can imagine, okay, even if you have, the sun, which is kind of the center, at least for us, the Earth flies around it. Well, the electrons are kind of doing the same thing. And they have various orbits or shells or levels that they're flying around with. Now, electrons are negatively charged particles. So they are the opposite, okay, charge of a proton. Now, they are actually much, much smaller than what we see in terms of protons. And here I am referring to in terms of their mass. So they're tiny in comparison to a neutron or a proton. Now, they always orbit the nucleus, okay, or the shell, or the levels that we call, around, okay, and in a circular pattern or in a randomized pattern, so not necessarily circular, okay. Circular just means that it's around it, okay, in that vicinity. And it will take on various shells, okay. It might be closer to the actual nucleus or might be further and further, okay. The further they go, they might get a little bit more energy to get kicked out of there. So they orbit the nucleus. Now, a neutral atom, which I designate here and I put it up in bold, has the same number of protons and electrons, and that is typically in their normal state. So they will be neutral in general. And if you say an atom, then we typically mean that it is neutral. So you can say atom or a neutral atom, okay, and they will mean identical thing, which means that the number of protons that it has and the number of electrons that circulate around the nucleus is identical. Now, if those electrons that you have, and all of a sudden, the one of those electrons, okay, gets added into the orbits, right? Or maybe more than one, or maybe, okay, one of those electrons kind of just disappears out of the orbit, goes somewhere else, and doesn't like it there anymore. So if you're going to have less electrons or more electrons than the number of protons you have, then we refer to that as an ion. All right, so that's what we have there. Now, there's a few things that I wanted to mention. So now we have a nucleus. Inside of that nucleus, we have protons and neutrons. Okay, it's circling around. We have all of these wonderful electrons, okay, that are going around, okay, at various shells or levels, okay, depending on how many you have and which element you are discussing. So there are a few things that we should kind of know as well. So one of those things is kind of the ground state. Okay, so what is this ground state? Okay, when we're talking about these electrons, well, it's the lowest energy level that we have. So it is the lowest energy level, okay, or shell that the electron is going to be, okay, kind of filling in, right? So if you have this and it's kind of in the center, and then, the electrons are kind of going all over randomly everywhere around, okay, its ground state is its lowest energy level that it can take, okay? And then it can kind of jump over and it can get excited, okay? So if it gets excited and jumps over into another state, another shell, another level, well, then we call this the excited state, okay? So not the ground state, but now the excited state. So if it absorbs energy, as you can see there, and jumps a shell, okay, or a level to a higher energy level, then we call that an excited state of the electron. And the ground state is its lowest energy level that it can take on. Now, there are many models that we have. Now, one of the models which you should be familiar with as you kind of walk into nuclear energy components, that is the Bohr-Rutherford model. Now, in the Bohr-Rutherford model, and I'll try to explain kind of what this is, these electrons, we typically will put them as a dot, and protons the same thing, and we kind of draw these nice circles, but they're not really perfect circles, right? These are just kind of abstractions, okay, so that it makes us understand these things easier. Now, in the Bohr-Rutherford model, the number of electrons that you can have in each kind of shell, okay, or each level, or each energy state, okay, is kind of figured out through a process. Now, it actually comes out from solving some formulas, which I don't want to get into here, but it gives us a nice model. It says that in any state or level, right, and you'll have level 1, level 2, level 3, and 4, and 5, you can only typically have so many electrons, okay? So it can only get filled with so many, and then they'll get kind of jump over to another level, so they'll be in a little bit of a different state. So let's try to illustrate these, okay, through carbon. And you can illustrate this through many other ways, okay, as well. Now, the first thing that I'll mention is if you take any element, okay, so let's say if this is carbon right here. So as I said, it is actually the number of protons that you have, okay, which defines what element we're talking about. And the number of protons is captured by the atomic number. So the atomic number, okay, so of that atom, it just tells us how many protons do you have. So it doesn't care about neutrons inside, it just cares how many protons. And the fixed number of protons it carries actually defines what that element is. And if you go into any periodic table, so here's one which I took a look at. So this is from, okay, the American Chemical Society, but you can find these all over the place, okay, and they're written, okay, in various forms. So if you think back, okay, again, so in terms of hydrogen as you're starting off, so this atomic number, okay, which is kind of given in here, so 1, here you see a 3, here you see a 4, it's written in various different forms, 11, 12. So that atomic number just means how many protons does that element have. All right, so that's what it is. Okay, and now the other component that it carries, and this is the same thing, you see this all over the place. Okay, there's another number which is associated. It's going to be bigger than the atomic number that you have, and this is all over, from calciums, everywhere you see this, right, on the actual periodic table. Well, what is this? So within here, I put the atomic number, okay, and it's smaller here, and then I put the atomic mass up above here, right there. Now, what is the atomic mass? Well, the atomic mass is the total number of protons and neutrons that you carry inside a nucleus. Because remember, the nucleus has both protons and it has also neutrons. So both of them combined, okay, nucleons, right? So how many nucleons are there? So carbon, for example, will have 12. Now, very often what you will find is that the number of protons that you carry is going to be kind of the same as the number of neutrons. So if you had, 6 protons, if you add another 6, then obviously you get 12. But this is not always the case. You sometimes will have in the nucleus, okay, the number of protons won't change, but the number of neutrons may change. And the number of neutrons that you have, okay, now starts to tell us about the different isotopes of that particular element, okay? So that atom that we're talking about, so inside of the nucleus, how many protons and neutrons do you have? And the number of neutrons that you carry, okay, so different numbers will mean that you have a different isotope. So the regular ones, so there's ones which dominate nature completely. And then there are ones which have more neutrons, okay, or less neutrons within. So you see that quite a bit, okay, happening. Now, before I jump into these different types of isotopes, right, so that you have and try to explain it a little bit further, I do want to go back to this Bohr-Rutherford model, okay, and then describe this 2n to the 2, because what does that mean? So within here, so if you take carbon, for instance, okay, so if you take carbon, and I'm going to try to draw this, and we of course try to approximate these by circles, but they're not really circles. So within here, you might have 6 protons, right? So 6 protons, I'll put a little plus because it's positively charged, and it might have 6 neutrons. Now, neutrons don't really have a charge, so I'm not going to put anything in there, okay, so they're neutral. And that would be in the center. And now, around it, we have these electrons which are swinging around. And they have different orbits, okay? Now, again, these orbits, this is drawn as circles, okay? Sometimes, as you see, orbit number 1 or level number 1, okay? Orbit number 2 or level number 2. And, so this keeps swinging around. Well, these orbits are randomly kind of going around, okay, this actual nucleus within here. And they're filled up with electrons. So these things are just firing off, and they're somewhere around here, okay? So these electrons, they can be at every level. Now, what happens is that the ones closest get filled up at first. But how many can you have within here? Now, they're not nicely circling around. They're just kind of all over. And remember, it's three-dimensional. So how many of these do you have in here? Well, so if you take carbon, and I'm going to assume that this is an actual neutral atom, right? So it's not an ion, so it doesn't have more or less. Let's assume that it has the same. So in this case, if I would take this, if I know that it has 6 protons, it's going to have 6 electrons in here. Now, where are those 6 electrons? Well, they're orbiting around here, all the way around the nucleus, okay? So they're going all over the place. And this model, the Bohr-Rutherford model, just tells us in each orbit, how many can you have here? So it turns out, so if you take a look, so 2n to the 2. So in the first level, now that first level is this first level right here around the nucleus. So in that first level, so what you will have is, you're going to have this many electrons. This is the maximum number of electrons that you have. Level number 1, so n stands for the level. Okay, and you have 1 squared, which is just 1, okay, and that means times 2, which is 2. So I am having, okay, only 2 electrons floating around in here. Now, very often, okay, in these Rutherford Bohr models, they might be just little dots, and then sometimes they're grouped in together, so just depending on how they are, right? So I don't really care how, you can put them in here. For me, the interest is, do you understand that these electrons are just floating around here? And you can't stick more in here, so you can't put another one, and then another one, and another one, okay? It won't happen. So in nature, what happens is that if you do have more, okay, they'll jump over, okay? And, they'll start filling in another level. Now, in that second level, what you have, so in level number 2, so if this is 2n to the 2, this means 2, well, level number 2. And all of a sudden, well, 2 squared is 4, and now 4 times 2 is going to be 8. So that means is that within this level right here, so as you're going around here, you can now have 8 electrons in there. And if it's carbon, okay, so notice that within here, so well, we have a 6 total. So, how many total electrons would you have all the way over here? So as you're going through, well, I've already put 2, okay, into my first level. So that means 4 are going to get placed into the other level. Now, again, so there's different ways trying to draw this out, okay, within here. So I'll like to separate them out, and then I'll start to combine them. But if I only have 6, well, then I would fill 2 within here, and then I would fill in 4 within here, and that's going to make 6. And so you wouldn't really have that extra level in here. So this level would have been gone. Those are the only 2 levels that you have. But that model, obviously, as you keep going and going, doesn't have to be carbon. You can take a gold, which has quite a lot of electrons. So within there, you keep filling out these particular shells or levels, okay, to the maximum amount. So if you keep going, this is, my apologies, this is squared, 2 to the third, so the third level now, all of a sudden, 3 squared is 9 times 2 is going to be 18. So you can now fit 18 electrons in the third level, and so on. So you can keep filling these up, okay, until you put all your electrons. And this gives you a sense of where the electrons are, which orbits there are around that particular atom, right? And they're circling around. And it's primarily just empty space that you have. These electrons, okay, are randomly, okay, all over the place. So that comes in from that Bohr-Rutherford model. And again, so, you should be very aware that you have an atomic number, which just tells you the number of protons, an atomic mass, okay, which tells you how many protons and neutrons that you have. However, what you will notice is in periodic tables, you notice that, wait a minute, okay, these are not fixed numbers, 6.94, 9012, 2431. Well, I can't have 0.31 of a neutron in there. So, you start scratching your head and you start saying, well, what is this? Well, this is where, on average, this tells you on how many neutrons will you have. So these numbers tell us, on average, how many actual neutrons and protons combined you have. Now, of course, some of them dominate. So within here, so for instance, if you notice hydrogen, which has 1.008 as its mass, atomic mass, so that means, well, hold on a second. So there's a proton, and on average, I only have one proton. I don't have any neutrons, because if I had another neutron, that would be 2 at least. So in the nature, it is actually true that most of the time, the most common isotope, okay, that we have of an atom really just has one proton for hydrogen. But it can also have 2, okay, and it can also have 3, okay, in terms of the total number of nucleons, protons and neutrons. So I want to talk about this isotope and give you a sense what this means. Protons will never change, right? So if you have 5 or 6 protons, well, 5 is a completely different element than 6 is. And you can look those up, okay, within your actual periodic table. So now here it is. So for hydrogen, what you see is, and I want to just illustrate this and bring the concept of the isotopes in here. So hydrogen, most commonly occurring, has only one proton and no neutrons, right? So I'm going to just highlight this in. Now this has a certain name. Now, I forget these names as well. So this is protium, okay? And this happens most commonly in nature. In fact, it happens, very close to 99.99% of the time, where a hydrogen isotope has no neutrons and only one proton. So this particular isotope, that's what it has. Now, a different isotope, it's still hydrogen because it still has only one proton. However, it may have also one neutron. So that's a different isotope that you have, okay? And this one is called deuterium, okay? So as you can see there. Now, this one is also found in nature, but very rarely. And notice that the atomic mass here would have been 2. So very dominantly, you have an atomic mass of 1, which just has one proton. Okay, and very rarely, sporadically, it will have an atomic mass of 2 with the proton and the neutron. Now, of course, if you take the average, if 99.99% only has 1, then on average, it will be just ever so slightly bigger than 1 in terms of your atomic mass. But one of them dominates. So you can't have, point something of a neutron inside of the nucleus. You either have it or you don't, okay? So within there. Now, there is one, again, it's not very common, but there is tritium, and tritium has one proton and 2 neutrons. That's a different isotope. So now we have 3 isotopes. Isotopes have the same number of protons, but possibly different number of neutrons. So you have 3. Now, this one, so tritium, is pretty much mostly man-made byproduct, and it happens in kind of nuclear reactions, which is kind of and it is radioactive. Okay, so this particular isotope is radioactive, and this is where the nuclear energies come in, okay, and understanding of nuclear physics, okay, slowly trickles in. So from chemistry back into, although chemistry is really a branch of physics. So these are 3 different isotopes that we have. Now, I do want to talk about this word radioisotope, okay, to finish off this particular video. Something that you should be aware of. So radioisotope, so I've mentioned isotopes, right? So isotopes are basically atoms that we have. Although atom, okay, when we mentioned, just a regular atom, it can have different isotopes. So hydrogen will have kind of 3 different ones, and it will depend on how many neutrons they have. They're still hydrogen, but it's a different isotope. Okay, and so that's what we would have. Now, radioisotopes are the ones which are unstable. So these ones, or these guys or gals, okay, are unstable in here. And they're unstable isotopes, meaning they can't hold that form. Okay, they don't like it. And when they don't like it, they're basically an isotope which becomes unstable, and it starts to change its structure, and it releases its energy because it can't stay in that form. So that release of energy, so this is what you see here, so it changes its structure and releases its energy. That energy transfer, so the energy inside, that unstableness, okay, starts to transfer, and it gives off nuclear radiation. Nuclear because it's coming from the actual nuclear components, nucleus of that atom. And that now energy starts to transfer out. Now, please note, nuclear radiation is different than thermal radiation, which is kind of transfer of heat through the vibrations that you have, and it's given off, and it's mostly, okay, in infrared. It is electromagnetic waves, okay, but they're kind of different. So in the nuclear radiation, so what you see, and this, you're going to be learning on this further, this is just an introduction. This is the release of the particles or electromagnetic waves which are coming from the unstable components of the actual isotope. So this is now radioisotopes that we have. And it releases these out, it kind of transfers those out. It is much different than thermal radiation. Both radiations are transfers of energy. Nuclear is the transfer of energy from the actual nucleus component of the unstableness of that atom, while the thermal energies, okay, are through the actual heat, okay, and the kinetic movements of the various particles that you have. So this is the introductory video. Welcome to nuclear physics, okay, or nuclear energy, and you should be well versed in these terms, okay, for the next little while. Thanks for watching. Hope that you found this useful. Bye, everybody.